Okay, this is a book called Data Mining Techniques, and there's a free chapter that's available on the internet, and I think it's chapter 19, and it's about an important concept or topic called derived variables, and this is important for your group projects. Basically, it's how to transform some of the variables that you have or create new variables from old variables. And they're going to use a sample data set having to do with mobile phone companies, and they're trying to predict which customers are going to leave, go to another mobile phone company. This is actually old data, but anyway, there's a database. It's readily available on the internet. They call it churn, customer churn, in the mobile phone industry. And the author's name is Barry, and Mr. Barry says, creating derived variables is one of the most creative parts of the data mining process. If there is an art and science of data mining, creating derived variables is part of the art. Derived variables allow data mining models to incorporate human insights into the modeling process and allow data mining models to take advantage of important characters. Okay, anyway, so he says it's creative. So actually this data comes from is an old data set, and they call phones handsets, not smartphones. So I urge you to read the entire chapter, but I'm going to just go through it to kind of give you an outline of what it's about. Okay, so first he talks about single variable transformations. So standardizing numeric variables is one kind of transformation that we can do. And basically that means taking a variable and so the variable's average, let's suppose we're talking about people's heights, and suppose that the average height is 160. So what you do is you create a new variable that is basically the same as that variable, people's heights, but you center it at 0. So the way that you do that is simply you calculate the average. So suppose we have 100 people, and they all have different heights. But if we calculate the average, it's 160, for example. Then we take each person's height and we subtract 160. We subtract the average from each person's height. So now, the average of the original variable was 160. The average of the new variable will be 0. So that's the basic idea. So that's called centering. Okay, subtracting the average from each value of a variable yields a derived variable with an average of 0, and the scale doesn't change. Let's say the tallest person was 200 centimeters, 2 meters tall, and the shortest person was 150. So the range between 150 and 200 is 50 centimeters. And let's say we said the average was 160. So if we subtract 160, the average, from every person's height, so the person that was 150, if we subtract 160 from that, now that is equal to -10. And if we take the person that was 200 and we subtract the average from that, 200, so 200 minus 160, we're going to get 40. And so now the shortest person has been mapped to -10, and the tallest person has been mapped to 40. And so the range between those two, between -10 and 40, is still 50. So that means they say that they haven't changed the scale, but the average of the new variable is 0. So that's called centering. Now I think in Weka we can do that. So for example, we have the iris data set here, and the sepal length, the minimum is 4.3 and the maximum is 7.9, And I think that we can use a filter called center. So let's try that. So I'm hoping that the mean, which is currently 5.8, when I apply center, will go to 0. So yeah, the mean goes to 0, and the range should still be the same, but it doesn't look the same. Let's see. It's about -3, and it's about 3.5 here. Let's see if it is the same. Yeah, okay, so it's still the same. So the range is still the same between the minimum and the maximum. It's still about 3.5, but the mean has been centered at 0. Okay, so we can do that in Weka. Okay, the next thing is called rescaling. So currently the range has not changed, but sometimes what we want to do is divide the centered variable by its standard deviation. So I don't know if we talked about standard deviation. You can look it up. But if I want to do that, I will undo what we did. And I think it's called normalize in Weka. So let's see what they say. Anyway, I think that what they do is they divide by the standard deviation. So if that's true, then what will happen is currently the standard deviation is this, but the standard deviation of the new variable should be 1. So let's see if that happens. No. Okay, so the filter is called standardize, and now the mean is 0. Let me do it again. So this is before we've done any filtering. This is the data, the variable, and then we're going to, so the standard deviation is this, and the mean is this. So the mean is going to go to 0, and the standard deviation is going to go to 1. So that's actually a good practice to standardize a variable. So let's apply it so you can see that it worked. So some people use the word normalize, some people use the word standardize for this process. Okay, but the idea is that we subtract the mean, we already talked about that, and then we divide by the standard deviation, and this is the result. Now this is, as I said, this is a good practice to do this to data when you're putting it into a model. The only thing is that when you do it, you have to remember that when you're kind of interpreting the results, you have to remember that you did this to the data. So if you want to sort of figure out what the actual meaning is, you have to remember to undo it at the end. For example, suppose this was not sepal length, but this was people spending. So how much they're spending. So the average amount that was spent was $100 or $200, say. Okay, then you transform this, and then the average goes down to 0. So you'd say, you want to remember that you transformed it, because you don't want to, at the end, interpret whatever result you get and say, oh, it looks like the average was 0 when that wasn't the original variable. You have to take it back to its original form when you do the interpretation at the end. Now there's one more that Weka has, and that's also common to use, but I don't think he discusses it in this text, and that is normalize. So let me undo here, and let's do normalize. What that's going to do is it's going to make the minimum 0 and the maximum 1. So it's going to map the entire data set, which currently is between 4.3 and 7.9, to the interval between 0 and 1. There's nothing particular that we can say about what the standard deviation will be, and nothing particular that we can say about the mean either. But of course, the mean will be between 0 and 1 because the minimum and the maximum are between 0 and 1. But anyway, let's just try this one. So the minimum and maximum are 0 and 1. The mean is in between there, and the standard deviation is this. So that's another process that you can apply. That's as good as the as standardizing, as the Wecker standardizing formula. Okay, another thing they talk about. So by the way, he calls it rescaling. I think that was the standardizing one. He calls it rescaling here. Okay, another thing is to take a numeric variable and convert it into a percentile. Now, I haven't been able to see, I don't know if Weka has a filter for this, but you could do it, say, you could do it in Excel or something like that, and then enter that variable into your data set. But anyway, the idea is, suppose that, for example, you're applying to universities and you have to take what they call the SAT test, and suppose that the lowest possible score is 200 and the highest possible score is 900, and suppose you get an 800, and you could convert that to percentiles. For example, suppose that 800 was the 90th percentile score. What that means is that you got an 800. That means if it was the 90th percentile, it means you did better than, that score was better than or higher than 90% of the scores. So you converted 800 into 90th percentile. So you can do that, and he says that that could be a good idea. So that's taking a numeric variable and converting it to a percentile. It seems like it would be a good idea, and it should improve the idea. What we mean by a good idea is that it improves the accuracy of your model. Okay, what else is there here? You can turn counts into rates. So I'll let you read about that. That's a pretty simple idea. Relative measures, that's percentile is an example of a relative measure. There are some other ones, you can read about those. Now, replacing a categorical variable with a numeric one. Okay, so that's another, can be useful, especially for models that need to work with numeric data and can't work with categorical data. So then it's very useful to be able to do this. He warns us not to just, let's suppose we had a variable called state, and suppose that you had like the American states. So, for example, suppose we had something like, let's take another example. Suppose we had a variable called beer, and the different possible beer preferences are Asahi, Kirin, Sapporo, and Suntory. Okay, just like going back to this book chapter, the state variable can take on all these different values. The beer variable, which is also categorical, can take on 4 different values. So suppose we have that, and suppose we have person number 1, and their beer preference is Asahi, and their name is Tomo. Okay, so we have a database that begins with these first 3 columns, and the second person is like this, and the third person is like that, and the fourth person is like that. So what you can do is you can create what's sometimes called a dummy variable. Sometimes it's called a indicator variable, and sometimes you call this procedure one-hot encoding. So anyway, the idea is we're going to get rid of this variable, beer, and we're going to create 4 new variables. So for every possible value of beer, in this case there are only 4 possible values. If we go back to the state variable, I think there are 52 states. So that variable state would have 52 different possible values. So you'd have to create 52 variables in this process. But here, for beer, if there are only 4 possible values for beer preference, then we have to create 4 new variables. So I created a new variable called Asahi, a new variable called Kirin, Sapporo, and Suntory. Okay, so once you do that, you can get rid of this. I won't get rid of it yet because I want to show how this works. So, so here's Tomo. He has ID number 1, Tomo, and his beer preference was Asahi. So what we see over here is that we put 0 for Suntory because it wasn't Suntory, 0 for Sapporo because it wasn't Sapporo, 0 for Kirin because it wasn't that, and 1 for Asahi. And then we have Daisuke, and his ID is 2, and his beer preference was Kirin. So with these new variables, we put 0 for Asahi because it wasn't Asahi, 1 for Kirin. That should be 0 for this one, and 0 for this one. And for Hiro, with Sapporo, so we put a 1 in Sapporo. Okay, so we don't need this variable anymore. I think I can hide this. Okay, so now this is what our data set looks like. So it doesn't have, before we only had 3 variables. It was ID, beer, and name, but now we have these variables, and this is what our data looks like this. So that's called, as I said, that's called creating a dummy variable, an indicator variable, or the whole process is sometimes called one-hot encoding. Now, traditionally, this was done in statistics, and in statistics, we would actually leave out one of these because you don't need this one. For example, I could get rid of this one. Let me just move it out of here. Okay, we don't need this one because if someone has 0, 0, 0, then you know that it must be Suntory. It must be a 1 here. So you actually don't need, this is kind of redundant information if you have 4. But anyway, in one-hot encoding, they include this in there, so we'll include it. Okay, but it's actually redundant. You don't really need that. So I'm not sure, but I think in statistics, they would say that it's redundant and therefore somehow might make the model less stable or less good or something. So it might be interesting to try doing this kind of encoding where you use all 4 and run your model with that and then get rid of one of them because, as I argued, you don't really need it. It's redundant. And then run this data. And I wonder if that would be an interesting study to do this on, say, 10 or 20 or 30 different data sets and several different models or several different algorithms and see if it turns out to be more accurate to include that Suntory in the data set or not include it. So here in this text, he calls it using indicator variables. Now we can do this in Weka. So we need a data set that has we don't usually do it for the class variable, okay, for the input variables only. So but I guess if you needed the class variable to be something, to be numeric, you might do it. But I'm not sure about how much sense that makes. Anyway, let's find a different data set. So let's try one. I think this one, contact lenses, has, this one is nominal, this one is nominal, this one is nominal. So this is nominal. So we have a lot of nominal variables here. And the idea is we want to take a nominal variable and make it numeric. So if we take a look at this data set, this is about, the classes are, the patient should be fitted with hard contact lenses, soft contact lenses, or should not be fitted with any contact lenses. And the first variable is age, and there's young, and this, so I don't know what these mean. So here it says it's a condition associated with the aging of the eye. Okay, so something about age. So let's just assume that this is young and this is middle-aged, and this is old, or something like that. Okay, so anyway, we have this categorical variable, age. Okay, it is categorical. Okay, and we want to convert it doing something like this. So we want to, since there are 3 categories in the age variable, we're going to want to create 3 new variables and get rid of the original age variable. So how can we do that in Weka? There's a filter called nominal to binary. Okay, because the new variable is only going to be 0 or 1, so that's a binary variable, right? That's what I did with the Asahi and Sapporo. The only values were 0 and 1. So it's going to be nominal to binary. Okay, and then you have to say which variables you want to apply it to. So do I want to apply it first to last? Let's say I just want to do it to the first one, just to make it simple. So you can write first just as first, or you can write 1. If you wanted it to do it to 2 variables, you could do 1 through 2, or 1 through 3. Or if you wanted to do just 1 and 3, you could do 1, 3, and maybe 4. You can. This is the way Weka works. But anyway, let's just do 1. Okay, and let's apply it. So what is it going to do before we do it? It's going to get rid of this variable, but it's going to create 3 new variables, and their names are going to be young, this, and this, or some variation of that, basically. So let's apply it and see that creation. Okay, so now we got rid of age, but now we have age equals young, this, and that. So we have these 3 new variables, which are each binary. Or I'm sorry, I should say they're each numeric. They're binary, but they're numeric. So it says numeric now, and the minimum value is 0, and the maximum is 1, but actually they only take on those values 0 and 1. There's nothing in between. And this is the data, so there's this many, there's 16 that are in the 0 category. So I guess that's 16 that aren't young. And there's 8 that are young, because that's the 1 category, which means young. Okay, so we can do that. And as we said, this is useful when you are when you have models that can't handle nominal data. Okay, this is called using indicator variables in this text. Replacing categorical variables with numeric descriptors. Okay, I'm not quite sure what he means here, but you should read through this and see what it's about. These are all really good tips for how to improve your model. Okay, we talked about binning before, or I think we called it discretizing a variable. So in that case, we have to go back to the iris. We have to go back to numeric data. And then we talked about binning or discretizing, so we could review that. So discretize, so this is the discretize, and let's just talk about doing the first one. Now we can either we can choose the number of bins that we want, or the number of intervals that we want to create. So we're going to take this is again taking a numeric variable and making it into a categorical variable, and we just divide up the data into intervals, and so let's see that happen. Let's not have so many intervals, actually. Let's just make it 4 and apply it. And now this variable sepal length is no longer numeric, it's nominal. And so the first possible value is in the interval from minus infinity to 5.2. And there are 45 pieces of data in there. And then from 5.2 to 6.1, there are 50. And here to here, there are 43. So it's a categorical variable now. So let's go undo that. Look at some of the other options that you can use here. You can let it, so we chose to have 4 bins, but you can let it run some kind of algorithm that kind of decides maybe what's the best number of bins. So let's see what happens when we do that. Let's click OK and apply that. Now it only finds it's decided that 3 bins is the best way to do this. And notice that these 3 bins have somewhat near the same number of elements in each one. But the bin sizes are not going to be, the bin widths are not going to be necessarily the same. So this is this length. So obviously that's true in this case. This is from minus infinity to that. So that's not going to be equal to this one. So anyway, that's one option. Let's undo that. Let's see what other options there are. Instead of find bin numbers true, let's set it back to false. And this, I'm not sure exactly what that does, use bin numbers. And then here, you can try and force it to use the same, to try and to make the widths of the widths of the bins don't have to be equal, as we just saw when we let it find the bin number. So you can let it try to make the bin widths so that they each have approximately the same number of data points in each bin. So let's try that. So we can use true, and let's try it. Did we? Yeah, okay. So now the number of bins is 4, and the number of elements is not exactly the same, but it's supposed to be close. So this is a discussion of binning. So we can have the widths of the bins are equal. So this is our, we have bins now that are approximately 54. This is length 54, this is length 54. But you can see that the number of elements in here is far more than the number of elements in here, or the number of data points in here. So that's not exactly the best situation. So here he says that quantiles are generally more useful than equal bin widths. So quantile, I guess, means, means that the bin widths are no longer here. You saw that if I made the bin width like this, then there's virtually no data in here. And even if I extend the bin width, this last bin width, to be from here to here, still there's virtually no data in there. Even if I went down to here, there's virtually no data. So he extends the last bin length to here. So now it has approximately the same amount of data as this one does, and hopefully this one has approximately the same amount of data that this one does. Notice that this is lower, but it's longer, so hopefully the total number of data points is approximately the same, and that's what we tried to achieve here. In fact, that's fairly true here. Okay, so you can do that. And he suggests that that's generally a better approach. Okay, then finally let's skip down to combining variables. So this is also very important. In fact, this is usually what I think of when I talk about derived variables. So what you can do is take, for example, suppose you have the number of teachers in a school, and you have, let's say we have a survey of 500 different universities, and we have the number of teachers and the number of students in the school. But an interesting ratio would be the number of teachers divided by the number of students. That would tell you how many teachers there are per student, or vice versa. And that could be an important predictor of, for example, how good the school is, or how well the kinds of jobs that students get after graduating, and so on. So that would be important, and that just having teacher or pupil, neither of those necessarily, the number of teachers or the number of pupils, would be indicative of how good a job the students are getting when they graduate. But this ratio might be predictive. So we might want to create this variable, which is very simple, right? You just take the number of teachers divided by the number of pupils, and you calculate that, and that could be a new variable. So that's the idea here. So he says oftentimes it's dividing one variable by another, but it could be products of two variables, or sums of two variables, or differences. It doesn't have to just be two variables. It could be several different variables that are included in the calculation. Another important ratio is like the price to earnings ratio. When you're talking about a company, let's suppose you're talking about Toyota stock, and the price is $1,000 per share, and the earnings is the overall earnings of Toyota in a year or in a quarter. So that's going to be millions or billions of dollars, I guess. But the price per earnings could be an indication. This ratio might be an indication of whether someone should buy the stock or not. In other words, this is what investors look at. They look at the price compared to the earnings. If the price is very low compared to the earnings, that might mean that you should buy that stock because it's underpriced. So that might, and not just whether you should buy it or not, but it might be an indication of, it might be important in your model. So, but that variable is not there initially. So you'll have the price of the stock, and you'll have the earnings of the company, but you may not have the price divided by the earnings. So you'd want to create a new variable that and include that in your data. So another example is the body mass index. So this was developed in the 19th century by this person. But anyway, what is it? It's defined to be the weight in kilograms divided by the square of the height in meters. So for example, suppose that someone is 1.8 meters tall and their weight is that. So you take this divided by the square of this. So the square of this, I don't know what it is, but it's less than 4 because this is less than 2. Let's say it's 3.5 or something. So you take the square of this and put this and you form the ratio of this divided by the square of this. So that's 86 divided by 3.5 or something. Let's say 86 divided by 3, it's about 30. It's actually, they say it's about 26.5. So this person, their BMI is 26.5. Because anything more than 25 is considered overweight, such a person should consider going to the gym. And it turns out that BMI, or this is gives you a kind of definition of obesity. If somebody's over 25 BMI, they're considered obese. So anyway, obesity is a predictor of diabetes. So height is not a predictor of diabetes, and weight is just slightly a predictor of diabetes. But this ratio that we defined is a predictor of diabetes, a strong predictor of diabetes. So having these two variables separately is not the same as creating this new variable, which is, remember, how did we create it? It was the weight divided by the square. So that's a somewhat unusual calculation, right? So that's why at the beginning he said this is a kind of a creative part of data science. So you have to think about how you should form this calculation. In this case, how you should form this ratio. So it's this divided by the square of this. Now, down below, he explains why this guy originally thought that it should be the square, why that was important. But anyway, that's part of what I guess he calls the art of data science, or the art of modeling. So that requires somehow some insight into the data. So here, this scientist had some insight into the data, and you can read what the insight is. Basically, it's that, I think it's that height is a linear measurement, but volume is, I would think actually it should be this cube of the height, but they're using this. I wonder if it wouldn't be better to use the cube, because height cubed gives you a volume, and weight has to do with volume. Anyway, whatever it is, he explains a little bit below. Here's another one called the wind chill index. So how is that defined? So I guess indexes in general are some combination of various variables, and indexes are used widely in economics. So how do they come up with those? Well, however they come up with them, they may be useful or important in modeling. Okay, he also talks about combining highly correlated variables. So sometimes variables are basically the same thing, and you usually don't want to include variables that are just replicas of each other. They might have slight differences, but basically the same thing. He gives an example here. He says the amount paid this month. So if you have to pay out bills, you're in a company and you have to pay out bills at the end of the month. So the amount that you pay at the end of this month is extremely close to the amount that you were billed the previous month, because maybe you received the bills at the end of last month and then you pay them this month. So the amount that you received as bills is going to be almost exactly what you actually pay the next month. So even though those are kind of two separate variables, they're almost exactly the same meaning. So in most cases, you wouldn't want to have both of them in your data set. Okay, I'm going to stop this discussion here, but I suggest that you read this carefully because it can help a lot.